Assalamualaikum, my name is AFRINA, and today me and my teammates from group CDCS2556C are going to present our wireless network project presentation for subject ITT640. So our group members consist of 4 people, which is Muhammad HAFIZUDDIN bin HAMSANI, myself AFRINA Syuhada binti JEFFRI Sam, next is AINA QISTINA binti AZIZ, and last one is WILLSON FREDO. For our project background, our project focuses on WLAN analysis and improvement at Bangunan CS1, Faculty Science, Computer and Mathematics at UiTM Shah Alam. So our project covers half of floor 1 and floor 2 of Bangunan CS1, excluding the bilik pensyarah. The current WLAN issues identified were multiple access points with open security configurations, usage of outdated Wi-Fi for hardware, inactive Cisco AP3 on floor 1, and limited wireless performance and capability. So, a wireless survey was conducted to evaluate the existing WLAN infrastructure, wireless coverage gaps, and network weaknesses and security issues. With that, we propose some WLAN improvement by reactivate and reconfigure existing access points, add one additional access point at floor 2, implement enterprise-grade wireless security, and develop a structured logical network topology for both floors. So the problem statement for our project covers 6 areas, which included security vulnerabilities, limited wireless performance, poor coverage and roaming, outdated hardware, inactive access points, and no centralized WLAN management. For the security vulnerabilities, there are several APs that are configured with open or non-security. Wireless traffic is not encrypted, and it increased the risk of eavesdropping and man-in-the-middle attack. For the limited wireless performance, Floor 2 AP2 only supports 2.4 GHz frequency with 20 MHz channel width. Um, there are also higher interference and lower network performance. For poor coverage and roaming, some areas have weak or insufficient wireless coverage, and also lack of overlapping coverage affects seamless user movement. Next is the outdated hardware. So some access point or AP still use the 802.1.11n, the Wi-Fi 4 technology, and it has lower throughput and efficiency compared to 802.11ac, which is Wi-Fi 5. For inactive access points, the Cisco AP3 on floor 1, which is on the surround area, is inactive, and it causes wireless coverage gaps in the surrounding area. And lastly, there is no centralized WLAN management, which there is no wireless controller available for AP management, roaming optimization, firmware update, and load balancing. Same just like before, for our project, we have 6 objectives to be obtained, which the first is analyze existing WLAN infrastructure, next to identify current network issues, design and improve WLAN solution, implement enhanced wireless security, restore inactive access points, and develop logical network design. So to analyze existing WLAN infrastructure, we need to evaluate EP specifications, signal length, frequency, and security settings on floor 1 and floor 2. To identify network current issues, we need to configure WPA2 Enterprise (EAP) authentication across all access points. Next is to design and improve WLAN solution. We need to detect wireless coverage gaps, security vulnerabilities, and hardware limitations. And to implement enhanced wireless security, we need to reactivate and configure Cisco AP3 near Surau Perempuan area to improve floor 1 coverage. Next, restore inactive access point. We need to develop a high-performance wireless network design with better coverage and reliability. And lastly, to develop logical network design is we need to create a network topology with proper IP addressing, VLAN segmentation, and IP routing configurations. The next part is the significance of our project. So the proposed WLAN designs provide the following benefits. The first one is enhanced network security. Is where we implement WPA2 enterprise authentication to protect user data and prevent unauthorized access. Next is the operational continuity. Is when we propose to reactivate Cisco AP3 near Surau Perempuan to restore wireless connectivity in previously weak coverage areas. Next, improve network performance by upgrading Wi-Fi 4 to Wi-Fi 5, access points for high speed, better capacity, and lower latency. Next is centralized network management. We propose to use a wireless controller for unified AP configuration, monitoring, and troubleshooting. Lastly, is complete wireless coverage, where we propose to deploy additional access point with strategic placement to remove coverage gaps and support seamless roaming across the area.
Before engineering our solution, we conducted a rigorous literature review of relevant standards. Legacy 802.11n or Wi-Fi 4, while functional, is highly inefficient in decent academic environments due to its narrow channel constraints. Therefore, we have established 802.11ac or Wi-Fi 5 as the absolute baseline for our proposed upgrade, leveraging its wider 80 MHz channel and multi-user MIMO capabilities to process simultaneous streams Looking forward, we also recommend integrating Wi-Fi 6 capable hardware for long-term future proofing. Crucially, our design mandatorily incorporates the 802.11k RNV standard to provide fast BSS transition enable reports, which are mandatory for seamless interfloor roaming. Next, our hardware analysis emphasizes enterprise tier ecosystem capability. We selected the Cisco Catalyst 9120 AX and HPE Aruba AP500 series to completely phase out or upgrade legacy component. For the core orchestration layer, we evaluate the Cisco 3504 wireless LAN controller to centralize policy enforcement and automate channel selection. The wired backbone will rely on managed layer 2 and layer 3 switches, such as the Cisco Catalyst 2960 X series, utilizing power over Internet Plus to safely power our distribution AP array directly through the network cabling. Furthermore, our physical review that verify that inactive Cisco AP3 near the Surau P can be safely reactive via the firmware restoration, maximizing resource utilization before the capital expenditure are met. Software orchestration form the protective shell of our wireless infrastructure. We integrate next generation firewall like the FortiGate or Cisco 5 Power series to execute deep packet inspection and strict content filtering at the edge. To successfully support WPA2 enterprise encryption, our system integrates the dedicated Radius server leveraging Microsoft Network Policy Server or Free Radius. This forces all incoming wireless requests to authenticate against the University Central Active Directory. Finally, the operational layer is rounded out by PRTG or SolarWinds monitoring software to actively track the packet loss, live throughputs, and latency profile across the board floors.
Now, let's move on to the network requirements for our proposed wireless design. For Floor 1, our goal is to provide reliable wireless coverage that supports high-definition video streaming, online learning platform, and voice-over Internet protocol communication. To achieve this, we set a minimum signal strength of negative 65 decibel milliwatt throughout all rooms and corridors. We also require a minimum signal-to-noise ratio of 25 decibel to ensure a stable and high-quality connection. Each connected device should receive at least 54 Mbps, while network latency should remain below 100 milliseconds and packet loss should stay under 2%. To meet these performance targets, Floor 1 will operate with 3 access points by keeping the 2 existing HP access points and reactivating the Cisco access point that was previously inactive. For Floor 2, the performance requirements remain the same because this floor also needs to support fast and reliable wireless connectivity. However, since Floor 2 contains a larger classroom and accommodates more students, we propose installing an additional access point. This increases the total to 3 access points, allowing the network to handle heavy traffic while improving load balancing during busy lecture sessions. For capacity, to validate these requirements, we conducted a granular device capacity estimation based on academic buildings metrics. Our network planning models assume that each proposed 802.11 AC access point can seamlessly maintain up to 50 concurrent highly active client sessions. On Floor 1, our expected user volume total roughly 55 concurrent devices distributed as 20 corporate laptops utilizing the high-speed 5 GHz band, 25 multi-band smartphones, and 10 academic tablets. Splitting this load evenly across floor first, 3 operational access points leave plenty of capacity to spare. On Floor 2, device density scales up significantly. Our matrix project up to 85 concurrent active units consisting of 30 laptops, 40 smartphones, and 15 tablets. Deploying only 2 access points under the old design force nodes to edge near their structural capacity thresholds. By adding our proposed third access point, we successfully distribute the traffic load, ensuring that no single access point experiences congestion or thermal throttling during high volume online exams or lectures. Next is the wireless coverage area. For Floor 1, the network covers approximately 3132 square meters. The western administrative offices, including the finance unit, are covered by Access Point 1, while Access Point 2 provides strong coverage along the central corridor. The reactivated Cisco Access Point 3 extends coverage to the eastern section, including the female surround, successfully eliminating the dead zones that previously existed in this area. For Floor 2, the coverage area increases to around 4160 square meters. Cisco Access Point 1 serves the Western Lecture Hall area, while HP Access Point 2 covers the Central Administrative Offices. To improve signal quality in the study rooms and surrounding areas, we propose placing a third access point more than 15 meters away from the existing units. This ensures the minimum negative 65 decibel milliwatt signal strength is maintained throughout the entire floor. Now, let's take a look at the building layout. On Floor 1, you can see the location of important areas such as Finance Unit, Bilik Kasper Sky, and Surau. This location helps determine the best position for the access points to maximize signal coverage while minimizing dead zones. On Floor 2, the layout includes classroom, lecture halls, offices, and study areas. Because these spaces are separated by thick concrete walls, wireless signals naturally can escape through them. This explains why the access points were no longer sufficient and supports our decision to deploy a third access point to maintain consistent coverage across the entire floor. Finally, let's look at the logical network design. In the previous network, the access points were connected directly to an unmanaged network without proper traffic separation. As a result, all users share the same network, treating both performance and security concerns. In our proposed design, we introduced a Cat6A shared Ethernet backbone, connecting the core switch on floor 1 to the distribution switch on floor 2 through a high-speed gigabit Ethernet link. Network traffic is separated into different VLANs, managed centrally by a Cisco 3504 wireless LAN controller. Students, staff, and guest users are each assigned to their own VLANs, improving both security and network performance by preventing unnecessary communication between groups. For network administration, we replaced the outdated Telnet protocol with SSH, allowing administrators to securely manage network devices over a dedicated management VLAN.
Assalamualaikum, I'm Hafiz, and right now I will be talking about the signal strength and coverage analysis of our survey. And therefore, we found out that during the close range on-site survey, the active nodes showed strong numbers right to the next antennas, which is on the floor 1 and floor 2. We found out a huge different comparisons that is affected by many variables. So therefore, on floor 1, the access point 1 registered an excellent negative 42 dBm, and the floor 1 access point 2 hit a negative 37 dBm. And right back up to the floor 2, the student Cisco access point 1 recorded an outstanding negative 35 dBm, while the office access point 2 returned to negative 39 dBm. But however, our technical analysis once again using is relying close range numbers because these measurements were taken within 1 meter of the hardware, so they did not reflect the performance at the actual room peripheries. They do not reflect the performance, and as the distance passes the 15-meter mark, the path loss formulas indicate that the signal sharply drops below the negative 65 dBm danger line. And so therefore, as for our simulation model proves that by deploying the reactivated access point 3 on floor 1 and after adding more access point on floor 1 and floor 2 and the proposed new access points on both floors, we normalize the signal grid and maintaining a highly stable and uniform negative 55 dBm to negative 65 dBm spread across all usable floor spaces for students and the staff. Next, moving on to signal to noise ratio. It is critical for maintaining high wireless data rates, and we found out that currently our 5 GHz infrastructure displays a strong SNR exceeding 30 dB immediately surrounding the active access points, largely because they are assigned to non-overlapping channels like 36, 44, and 55. But however, for floor 2's legacy HB access point 2 is currently trapped on the highly congested 2.4 GHz spectrum on channel 11. It faces severe interference from neighboring institutional networks and overlapping IoT device, which degrades the SNR in the administrative sectors. So our proposed solution leverage the wireless LAN controller to introduce an automated channel assignment. So therefore, this controller actively scans the RF environment in real time to dynamically shift all 6 access points onto the cleanest, lowest interference 5 GHz channels, and perhaps for even more access points assigned to the proposed topology for our survey is to ensure that our required 25 dB SNR baseline is met across the entire facility, especially for floor 1 and floor 2 of the CS1 building. So moving on to signal strength by access point. So I will be reviewing the precise diagnostic confirmations for each floor. For floor 1 of access point 1 is measuring at negative 42 dBm at 0.6 meters and will be retained and reconfigured to WPA2 enterprise. And for the access point 2, it is registering at negative 37 dBm at 0.3 meters and still be retained and upgraded to enterprise encryption. For the access point 3 that is inactive near this route, it is stated for complete reactivation and will be added with security alignment. Moving on to floor 2, our performing Cisco access point is measuring at negative 35 dBm at 0.3 meters and will be retained as our primary student network asset. And for the access point to our active unit, reading to negative 39 dBm at 0.9 meters, will be shifted away to open mode to enterprise authentication. And even more, we'll be planning to add even more access point to improve the network performance. So, and then finally, regarding the network performance, so to wrap up this technical analysis score, our ECHO simulation performance reports confirm excellent results for our proposed design. So here we can see that on the floor 1, our criteria pass rates hits for flawless 100% across data range metrics and round trip time constraint and packet loss parameters. And channel interference drops to 0. Now on the floor 2, despite the architectural complete challenges, the simulated network delivers a brilliant 99% pass rate for data rates and round trip time, with packet loss security contained below our 2% ceiling. And these metrics validate our layout choices and prove that design proposed will be successfully handled as student traffic load and for the staff as well.
In conclusion, our project provides a rigorous roadmap to transform the wireless infrastructure of Bangunan CS1 by taking immediate steps to enable WPA2 enterprise, reactivating the dormant Surround AP, and placing our legacy Wi-Fi 4 hardware. We neutralize our primary security and coverage vulnerabilities. Over the next few months, installing the Cisco 3504 wireless LAN controller and anchoring it to centralized radius server, we establish a seamlessly managed, highly secure ecosystem across the board floor. Long-term, this architecture leaves UITM beautifully positioned to transition to Wi-Fi 6E network, introduce isolate IoT segmentation, and explore agile cloud management platform like Aruba Central or Cisco Meraki. Ultimately, this design ensures a reliable, high performance, and enterprise secure wireless environment perfectly tailored to support modern academic excellence. Thank you. That's all for us.